This is the presentation for chapter number 10, the last chapter for Chem 111. So in this chapter, we're going to be taking a look at solids and liquids, or specifically phases. And a phase is basically a system where we've got two different phases of matter or types of matter that are in contact with each other, and it forms a well-defined boundary like ice and water. And so what we're going to do is we're going to first take a look at the forces that hold the solids and the liquids together. If we remember from the previous chapter, gases are in constant motion, that kinetic molecular theory, and that the particles are far apart. In this case, what we're going to find with solids and liquids is we're going to find that they're relatively close to each other, so there must be some forces that are holding them together. So the two forces that hold all compounds together are either intermolecular forces or intramolecular forces. We've been concentrating on the intermolecular forces that hold atoms together in a molecule. Now we're going to concentrate on the intermolecular forces, or the attractive forces between separate molecules. Okay, what we're going to find is the intramolecular forces are a lot stronger than these intermolecular forces, and that's why we get these phase changes. And when we take a look at the intermolecular forces, because they're relatively weaker, we get, like I said, we get the phase changes. So we're going to be taking a look at boiling point, melting point, and the amount of energy to vaporize um, a liquid to a gas, or turn a liquid to a solid, or getting a solid to turn into a gas. So what we're going to do is we're going to take a look at some of these forces. The first one we're going to take a look at is dipole-dipole forces. Remember back in chapter number 7, we were figuring out whether molecules were polar or not. And the reason we were interested in whether polar or not is these opposite ends of these molecules are going to be attracted to each other, or they're going to stick to each other. So if we take a look, we've got chloromethane and we've got dichloromethane, the boiling points of trichloromethane. And what we find is the boiling point of trimethylchlorine you would expect to be more polar. So it's going to have a higher boiling point, and so it would be greater than 40 degrees Celsius. The other attractive forces, remember in our continuum when we were talking about bond strength and we talked about going from ionic to polar to nonpolar, we can also have ion dipole forces. It's the attractive forces between an ion and a polar molecule. There's a lot of this interaction that takes place at the molecular or the cellular level, that basically you have little molecular motors, and where the polar end of a molecule will pick up an ion and actually transport it from one location to another, the sodium ion pump in the nerve cell, that there's a polar molecule that pulls the sodium and potassiums from one side of the molecule to the other. And then we can have the weakest of these, which are dispersion forces. And they're dipoles that are produced that because they're being induced, or they're being forced to be produced. And this can be produced by either an ion or two dipoles pushing near each other. And we can measure how well those electron clouds can be dispersed. Okay, again, you take two large atoms and you squish them, push them near each other. They're going to cause their electron clouds to distort, and they become partially polar. And so, what causes how well that molecule can be polarized, or that distortion of the cloud, is the greater the number of electrons, more diffuse, or the more diffuse electron cloud, okay, because it's bigger. So the dispersion forces usually increase with molar mass, because we assume molar mass means more atoms means more electrons. So it says, which of the following substances expects to have the highest boiling point? It's going to be the one with the largest or the greatest mass, which is going to be further down on the periodic table. So we'd expect the iodine, which has a mass of about 80 grams per mole, Fluorine has 19 grams per mole for single atoms, so we'd expect the iodine to have the largest. So if we take a look at what types of intermolecular forces exist between each of the following molecules, HBr is a polar molecule, so it's going to have dipole-dipole forces plus dispersion forces, but the polar dipole-dipole is going to be a lot stronger. CH4 is nonpolar, so the only thing it's going to have is the weak dispersion forces. And what we're going to find is CH4, methane, is found as a gas at room temperature. SO2 is a polar molecule because an unshared pair of electrons on the sulfur is bending it. And so it's going to have dipole-dipole forces. There's also dispersion forces, but again, they're relatively weak compared to the dipole-dipole forces. Okay, what we're going to do is we're going to take a look at a special case of dipole-dipole interaction. It's called the hydrogen bond, and it's specifically between the hydrogen atom and an NH, OH, or FH bond because of the high electronegativity of the oxygen, the nitrogen, or fluorine atoms. So this is, like I said, a special case of dipole-dipole that it's extremely dipole, and so these are a lot stronger than our other forces. And if you take a look at our molecules and you take a look at our graph, molecules of similar size, we would think decreasing molar mass would have a decreasing boiling point, but because of this hydrogen bonding, they actually get a big jump or increase in their boiling points or intermolecular attraction. So if we take a look at our list, it says which of these would we expect to have the highest boiling point? Well, it's going to be the one that's going to have the hydrogen bonding in it. So it'd be the HF or the hydrofluoric or the hydrogen fluoride or hydrofluoric acid if you actually dropped it into water. Which of the following would have that hydrogen bonding or that specialized? Would be the NH3 because it's the only one that has a nitrogen, fluorine, or oxygen in it. So we've got the intermolecular forces present in CH3, NH2 include which of the following? Well, it's going to have the hydrogen bonding because the NH2, the nitrogen in it. It's going to have dispersion because all molecules have dispersion. And this molecule is polar because of that nitrogen. Okay, remember it's going to form a trigonal pyramidal shape. And so we're going to have 1, 3, and 4. The only one that's not going to have is the ion dipole because we don't have any metals to form ions. So the intermolecular forces present in CO, it's not going to have hydrogen bonding because there's no hydrogen. Yeah, it's got oxygen, but it also has to have hydrogen. And so it's just going to have the dipole-dipole and the dispersion forces. Again, all molecules are going to have dispersion forces. They're the weakest. So in terms of their bulk properties, how do liquids and solids differ? Liquids and solids are similar in that they're matter composed of atoms, ions, and molecules. They're incompressible, have high densities, and they're different in that liquids have no fixed shape and the solids are rigid. They have really strong intermolecular forces. If we arrange each of the following sets of compounds or into an order of an increasing boiling point, silicon tetrahydride is going to be nonpolar. The HCl is going to be polar, and then the water is going to actually have two hydrogen bonds, so it's really going to have a high boiling point. So now we've got CH4, C2H6. They're all nonpolar. So now we go back to lowest mass to highest mass. And so the CH4 is going to be lower than the C3H8. If the melting point of water is 0 degrees Celsius, would you expect the melting point of H2S to be minus 85, 0 degrees, or 185? Well, it's not going to have any hydrogen bonds. Okay, so it's only going to be polar, which means it's going to have a boiling point that is less. And because Water has those hydrogen bonds. It's going to have a really high melting point compared to the H2S. And so we would guess that it's around minus 85 degrees Celsius because of those stronger hydrogen bonds. Now we want to explain why a hydrogen bond between two water molecules is weaker than a hydrogen bond between two hydrogen fluoride. Again, remember, fluorine loves electrons, so the hydrogen fluoride molecules is stronger because it's got a greater electronegativity. And so we're going to identify the intermolecular forces present in the following. So if we look at A, it's got an OH on it, so it's going to have hydrogen bonds. And it'll also have dispersion forces. B is just going to have dispersion forces. There's no hydrogen bond. It's not polar. Technically, A is polar, but remember, hydrogen bonding is a special case of polarity. And so C is going to have that dipole attraction and dispersion forces. Notice all three of them have dispersion forces, so make sure you always select that. And then remember, hydrogen bonding is a special case of dipole-dipole attraction. So now what we're going to do is we're going to take a look at the properties of liquids due to these dipole-dipole or hydrogen bonding interactions. And so if we take a look at water, water is the only substance that we know of that is actually more dense in its liquid state, or I'm sorry, and it is, yeah, more dense in its liquid state than its solid state. And that's why ice floats on top of water. Take a look, here's the graph of the density. And that has to do with the structure and what happens with the shapes of the hydrogen bonding. So what we found with water, which the following is not true with regard to water. Ice is more dense than liquid water. No, it's less dense. That's why it's floating on the top. Because of these interactions in liquids, we can have a surface tension. It comes from strong intermolecular forces. And so we'd have a high surface tension. Water's got a really high surface tension, so much that water striders or bugs can walk across the top of it, or we end up with a meniscus um, from the interaction. So which property of water allows a razor blade to float on it without sinking? It's surface tension. Kind of the consequence of that surface tension is we have cohesion and adhesion. Okay, adhesion is the attraction between unlike molecules. So if you take a look at the one on the left, the molecules are attracted to the glass on the side, kind of like a water in a graduated cylinder, that meniscus, and we always read at the bottom of the meniscus. Water's attracted to the sides of the container. Cohesion is when molecules are attracted to themselves. The one on the right is showing mercury. Mercury has such a strong cohesion that if you drop it out of the container, it actually forms small little beads, and mercury really doesn't flow, it actually rolls because it forms little small beads. Viscosity is a measure of a fluid's resistance to flow. So strong intermolecular forces are going to have high viscosity. You dump over a jar of honey and a glass of milk, the milk's going to spread all over the table and the honey's going to go out slower because the honey's got the higher viscosity. If we want to change the viscosity, we warm it up. If you want to get the honey to come out of the jar faster, you warm it up a little bit. So which of the following liquids would have the highest viscosity? Well, we're going to look for the one that's got hydrogen bonds and it's polar. And so if we take a look at E, the reason that it's going to have a higher viscosity than C, if you'll notice it's got an OH on either end, so it's going to form two hydrogen bonds instead of just one like in C. Which one of these would have the lowest viscosity? So it's going to be the one with the lowest attractive forces. And so it's going to be A. If you notice, it's got hydrogens all the way around the outside of it. So it's going to be nonpolar. It's just going to have some dispersion forces. So we're going to take a look at some test tubes with some oil in it. Okay. And when you go to get your oil changed, they ask you what type of oil you want. Normally you just say, well, I want the manufacturer's, and they'll go ahead and change it out. But the different values on the oil tell us their viscosity. And the higher the value, the higher the viscosity, or the slower it's going to flow. And so in the summertime, you want a really high viscosity so it doesn't warm up, but in the wintertime you want a lower viscosity because it's really cold and you don't want the oil so thick that it won't flow through your engine. So here we've got a table given several different temperatures of the surface tension and the viscosity. So if you notice as the temperature increases, the viscosity goes down. And you also notice there's a decrease in the surface tension. And that's because as the water reaches higher temperatures, the molecules are moving faster, kinetic energies, and so they overcome these attractive forces. And so the surface tension breaks down and the viscosity. So that's why we get thermal pollution. And in thermal pollution, the surface tension goes down, and those bugs that normally could ride on the top of the water have a hard time staying on the top. If we look at the viscosity, it's the same trend that we see with the surface tension. That as the temperature heats up, the viscosity goes down. So that's why when we're looking at the motor oil, that you want thicker motor oil in the summertime because it's going to thin out faster than in the wintertime. If you use too thick of oil or a high viscosity of oil in the wintertime, it'll sludge in your engine, which can damage your engine. So let's take a look at some phase transitions. You guys know these as boiling and freezing. And so here's a chart that lists pretty much most of the ones that we're going to take a look at. Most of them you're probably already familiar with. There's a couple we'll mention in a little bit more detail, that sublimation and deposition. But I think the four in the middle you're probably familiar with: melting, freezing, vaporization, condensation. And so if we take a look at the effect of the temperature on kinetic energy, we've got a bell-shaped curve because our temperature is the average of the kinetic energy. And if you'll notice, when we get our T2 is a higher temperature, even though it looks like the curve isn't as high, we've got more area underneath the curve at a higher energy. So that's why it's got a higher temperature. So when we go to take a look at evaporating water going from a liquid to a gas, we start to heat it up and it starts to condense, and it reaches a point where the evaporation equals the condensation. And this is said to be an equilibrium or dynamic equilibrium because it doesn't stop. It keeps moving once it reaches there, that it's going forwards and backwards at the same rate. So eventually, the vapor pressure of a liquid in a closed container depends upon the temperature. So to give you an idea of what's going on, we've got a frozen liquid in empty space, then we start to warm it up. As we raise the temperature, more molecules can escape. They're going to escape and return, escape and return. If you'll notice, our pressure starts to go up. And we can measure the height of this pressure in that mercury. We did this for gases with our manometer problems. So what feature characterizes the dynamic equilibrium between liquid and its vapor pressure? One, molecules are continually exchanged. That's why it's called dynamic equilibrium. and that's a constant vapor pressure at a constant temperature. So there's a direct relationship between the temperature and the vapor pressure. So what we find is the boiling point is the temperature at which the equilibrium vapor pressure of the liquid is equal to the external pressure. So water will start to boil when the vapor pressure equals the pressure above it. Okay. The normal boiling point is the pressure at 1 atmosphere. Remember our STP and standard condition for gas laws was 1 atmosphere. So the normal boiling point is the temperature at which that pressure reaches 1 atmosphere. And so we've got the boiling point of several different molecules. If you take a look, water is relatively high and mercury super high. So heat is added to boiling water. Explain why the temperature of the boiling water does not change, which is a surprise to a lot of students. So when we heat it up, it increases the kinetic energy, and molecules have enough to escape. Okay? The escape of the molecules requires additional energy, and so the temperature remains constant. As long as you've got liquid molecules in there, that temperature is going to remain constant. And so it says identify two common observations indicating some liquids have sufficient vapor pressure to noticeably evaporate. The amount of liquid in an open container decreases, or we can smell the vapor of some liquids like perfume. How does the boiling point of a liquid differ from its evaporation? At the boiling point, the vapor pressure of the liquid is the same as the atmospheric pressure. But water will evaporate at all temperatures. Okay, so during evaporation, the vapor pressure of the liquid is less than the atmospheric pressure, but it's slower because remember, it's an average kinetic energy, so some of those molecules just have enough energy to escape. At the boiling point, all the molecules pretty much have enough energy to escape. Okay, so we've got a list of compounds and we want to know which would have the lowest vapor pressure at room temperature, which means which one is it the hardest in order to turn into a vapor. And the one that's the hardest to turn into the vapor will be the water because it's got the highest boiling point. You have to reach 100 degrees Celsius before all the molecules would have enough energy to escape. And so the higher the boiling point, harder to vaporize. So we're looking for at water. We're looking for the highest vapor pressure at its normal boiling point. This is kind of a trick question because it's not saying any specific temperature. It's saying if we have each of these at the degree listed, all of these would have its normal boiling point would be the same or would be if we had that temperature, they would all be able to vaporize and then would have the exact same pressure, which would be the atmospheric pressure. So which of the following properties indicates the presence of strong intermolecular forces? A low vapor pressure. Okay, remember, weak intermolecular forces means you would have a lot of vapor. It says use the graph of vapor pressure to determine the normal boiling point. Well, we need to find where the normal atmospheric pressure is. So going back to gas laws, we said that was 1 atmosphere, 760 millimeters of mercury, 760 torr, 101.3 kilopascals. This is in millimeters of mercury. So we're looking around 760 millimeters of mercury. And so if we use our graph, what we're going to find is going to be about halfway between the 60 and the 70. So it's going to be 64 degrees Celsius. It says use the graph of vapor pressure to determine the normal boiling point. Now it's in atmospheres, and the normal pressure at sea level is around 1 atmosphere. And so if we go back down, what we notice it's going to be right on the 90, and so we're going to get 90 Kelvin. The molar heat of vaporization is the amount of energy required to vaporize 1 mole of a liquid at its boiling point. We've got an equation, the Clausius-Clapeyron equation, which can use to be calculate the heat of vaporization using the ideal gas law constant, the temperature. So which of the following substances is expected to have the highest molar heat of vaporization? It's the one with the strongest intermolecular forces. So it's going to be water. So here's two alternate forms of the Clausius-Clapeyron equation at two different temperatures. And we can calculate the heat of vaporization. We'll use a modification of this equation, Chem 112, to not to find the heat of vaporization, but we can actually find the activation energy for a chemical equation. And we're not going to worry about putting some numbers in and calculating out the answer to it. The interesting thing that's been found quite recently is there's this thing called the critical temperature, and it's the temperature above which a gas cannot be made to liquefy no matter how great the applied pressure. See, when we went to go to the moon, we needed to figure out some way in order to store oxygen in a more dense, smaller space. And so we figured out how to liquefy oxygen, which we call LOX, LOX. And in that research, what they found is they had to have the right temperature and the right pressure in order to do that, that they couldn't just keep adding pressure, adding pressure, adding pressure, and have the gas turn into a liquid. So what they found is there's a minimum pressure and there's a critical temperature in order to for liquefaction to take place, or that is turning a gas into a liquid. We found that, and now when you go to buy propane gas, you buy liquid propane. Um, when I was in elementary and high school, you didn't buy liquid propane. They just filled up the tank as tightly as they could with the propane gas. So if you notice, we've got melting and freezing, solid to liquid and liquid back to solid. And so the relationship between the intermolecular forces in a solid and its melting point, I think we could probably logically figure out if you increase the intermolecular strengths, then you're going to get an increase in the melting point. So the melting point of a substance increases as the strength of the intermolecular forces increases. And this is true for everything we're talking about. We just got to be careful about that vapor pressure thing. High vapor pressure means it's got weak forces because a lot of the molecules can escape. So the molar heat of fusion is the energy required to melt 1 mole of a solid substance at its freezing point. The molar heat of sublimation, which is something that you may not be as familiar with. And the molar heat of sublimation is the amount of energy to go directly from a solid to a gas. Again, here's that example. If we take the heat of fusion, the heat of vaporization, and add them together, we end up the heat of sublimation. And that's why when it snows, even if it stays below freezing point, the snow will eventually disappear because it will sublimate. So a phase change from a gas directly back to the solid phase isn't sublimation, it's deposition. So we've got acetic acid has a heat of fusion of 10.8 kilojoules per mole and a heat of vaporization of 24.3 kilojoules per mole. What's the expected value for the heat of sublimation? So the heat of fusion plus the heat of vaporization equals the heat of sublimation. And so we would just add the two together and we'd end with 35.1 kilojoules per mole. And again, here's an example of solving for the heat of vaporization for carbon tetrachloride. Notice it's a plug and chug type problem. We just plug into the formula, but just like when we were doing the energy um, in chapter number 6 with the electrons, we just got to be careful of putting inverses. Luckily enough, this one isn't squared because remember it was the constant times 1 over n squared minus 1 over n squared. So here's an interesting. It takes longer to cook an egg in Fort Davis, Texas, altitude 5,000 feet above sea level, than it does Boston at sea level. Well, at 5,000 feet, the atmospheric pressure is lower, and so the water is going to boil at a lower temperature, which means it's not going to give as much energy to the egg as quickly, so it's going to cook slowly and for a longer time. So perspiring is a mechanism for cooling the body. As long as the air surrounded body contains less water vapor, then it's going to evaporate and it's going to cool the body by removing the heat of vaporization. And that's why when in the summertime, when it's hot and muggy outside, it even feels hotter because it takes your body more energy to evaporate the water off of your skin because there's already a high amount of vapor already in the air. So it says explain why the molar enthalpies of vaporization of the following substances increase in the order. Okay, remember we're going to go from smaller molecules to bigger molecules. So the dispersion forces increase with molecular size. So you would figure that homologous series means that they all have the same elements in them. That you would expect that the vapor pressure or the molar enthalpies of vaporization would take more energy to vaporize C3H8 than it would CH4. And so methane's nonpolar, and so it's got relatively weak dispersion forces. Ammonia and water are both polar molecules, but one, the electronegativity of the oxygen is greater than the water, and it's also got two hydrogen bonds instead of just one hydrogen bond. So which contains the compound listed correctly in order of increasing boiling point? We're going to go from nonpolar to polar to hydrogen bonds to finally ionic. Remember, ionic compounds have metals in them. And so we're going to end up with A, that nonpolar nitrogen gas. CS2 is going to be polar. Then we're going to have water with the hydrogen bonds. And then we're going to have KCl, which is ionic. So what we're going to do is now we're going to take this idea of phase changes, we're going to put them into some diagrams so we can visualize them. So here's our classic heating curve. Okay, if you take a look, we got a solid go up to A, and then between A and B, we got the melting point. Notice the temperature stays the same as long as there's solid and liquid present. Then we go from B to C, we're going to heat up the liquid, and when we finally reach the boiling point, it's going to turn from a liquid to a gas, and as long as we have liquid and gas present, that temperature is going to stay the same. So let's take a look at a couple problems. It says, what mass of water would need to evaporate from your skin in order to dissipate 1.7 times 10 to the fifth joules of heat from your body? Well, the heat of vaporization is 40.7 kilojoules per mole. So that's going to be 1.7 times 10 to the fifth joules times, we got to convert that to kilojoules. So that's why I'm going to divide by 1,000. and then I multiply it by its heat of vaporization, or divide by its heat of vaporization. Notice the 40.7 is in the bottom. I end up with 4.17 moles. And we should be able to take 4.17 moles and convert it to grams of water, now that we're coming to the end of Chem 111. And hopefully you recognize that 18.02 grams per mole is the molar mass of water. So we'd end up with 75.2 grams of water. Okay, that's 75 milliliters of water to dissipate 1.7 times 10 to the fifth joules of heat from your body, which is um, basically about 170 kilojoules, which is about 60 calories. How much heat is required to convert 4.22 grams of liquid H2O at 23.5 degrees Celsius into steam at 150 degrees Celsius? Well, this is more than just one step. If you remember our phase change diagram, you can see at the top of your sheet that we're going to have to heat the water, we're going to have to turn it into steam, and then we're going to have to heat the steam to get the total energy. So basically, we're looking at that diagram at the top of your sheet. We're somewhere between B and C. Then we got to go from C to D, and then we got to go above D. So the heat of the water is MC delta X. If you notice, the heat capacity of water is given in joules per gram per degree Celsius. This Q equals MCAT. And so we're going to end up with 135 kilojoules. We're going to turn into steam, so we got to turn that grams of water into moles of water, because our heat of vaporization is given in kilojoules per mole. And then we got to heat that steam. And so our the heat capacity of steam is 2.09 joules per gram per degree Celsius. So that's why I had to divide by 1,000 to come up with the kilojoules. We're going to add all three of these together and we end up with 1,130 kilojoules. If we want to look at this and not have to do calculations, it says which of the following constants is or are needed to calculate the amount of energy required to heat water as a solid to, and to liquid as and just to heat up the liquid. So we're going to need the heat of fusion. We're going to need the specific heat of water as a solid because we need to heat up the ice. And then finally, we're going to need to heat up the water as a liquid. So we need 1, 3, and 4. Another way we can represent the phase change is what's called a triple point diagram. And this is pressure versus temperature instead of time versus temperature. And we have this thing called a phase change, or this is what's called a triple point diagram. And the interesting thing at this triple point, we actually have all three phases would be present. If you'll notice, as we go from left to right, we go from solid, liquid to vapor or gas. So the temperature and pressure at which three phases of water exist in equilibrium, it's called the triple point. And so the temperature is about 0.01 degrees Celsius and about 0.006 atmospheres of pressure. So we're going to look at the temperature at which water boils at 1 atmosphere. It's called the normal boiling point. We've already talked about that. And so it's going to be 100 degrees Celsius and 1 atmosphere, or 762, or 101.3 kilopascals. The temperature at which water freezes It melts at 1 atmosphere. Actually, doesn't the pressure change doesn't have much of an influence over it at all. And it's called the freezing melting point, and that's going to be B, and that's going to be at 0 degrees Celsius. Again, pressure of 1 atmosphere, but pressure really doesn't influence melting a whole lot. The temperature and pressure at and above which the properties of water vapor cannot be distinguished. This is above that critical temperature, so it's called the critical point, and it's way above the arrow. It's really high. For water, it's 374 degrees Celsius and a pressure of 73 atmospheres. So it says, name the phases that water will exhibit if the pressure is kept constant at 1.10 atmospheres, and it's increased from, that should be minus 10 to 110 degrees Celsius. And so it's going to go from a solid to a liquid to a vapor. Again, that should be minus 10 degrees Celsius. So it says name the phases that water will exhibit. Again, it needs to be from minus 10 to 110 degrees Celsius. So if we go across the bottom, if you'll notice, we go straight from the solid to the gas. And so this would be sublimation. So the temperature and pressure at and above which the properties of carbon dioxide cannot be distinguished from those of solid carbon dioxide. And what we're going to find for carbon dioxide, it is 31.7 degrees Celsius and 73 atmospheres. And we get this critical pressure. The cool thing about this is if you have carbon dioxide at this critical pressure, you can drop a coffee bean through it. And when you drop the coffee bean through it, the non-carbon dioxide being nonpolar will extract the caffeine out of it. It gets absorbed into the carbon dioxide. We can then bubble the carbon dioxide through water, and it'll carbonate the water, and it leaves caffeine behind in the water. So you have a highly caffeinated, carbonated water solution. Add a little bit of sugar, and you have a highly caffeinated drink, or you have an energy drink. So we're going to use the phase diagram for water. It's figure 10.31 in your book. And it says determine the state of water at the following conditions. And what I've done is I've labeled them on the diagram. So if it's 35 degrees Celsius and 85 kilopascals, we would expect for it to be a liquid. If it's minus 15 degrees Celsius and zero point 0.1 kilopascals, that's C, we would expect it to be a solid. And at 40 degrees Celsius and zero point 0.1 kilopascals, we would expect for it to be a water vapor or a gas. What we're going to do is we're going to combine sections 10.5 and 10.6 together to finish out Chem 111. And so when we take a look at solids, solids are either crystalline or amorphous. Crystalline solid are rigid, and an amorphous is not as well defined, and it melts over a range of temperatures. Crystalline solid would be an ionic compound, and amorphous solid would be something like a plastic. But all solids have unit cells, okay? And at the point of those cells, which gives the crystal its shape, is called the lattice point. And so there are 7 basic unit cells, and we could calculate the diameter and the shapes, and we'll leave that for another chemistry class. So an amorphous solid doesn't possess a well-defined arrangement, And one of those classic examples is glass. It's optically transparent, so it's somewhat organized, but it doesn't crystallize into a rigid state. And so what we find is if you ever look at an old house and you look at the bottom of the windows, you'll notice the glass is thicker at the bottom than it is at the top because the glass is going to flow or gravity is going to pull it down. And that's why when you see the old houses and you go, wow, someone's been throwing rocks through the windows. Well, no, they haven't been throwing rocks. It's just if the glass hasn't been replaced over a long period of time, it flows down. It becomes so thin that just the wind blowing can actually break the glass. So we've got tungsten is classified as a metallic crystal because it's made up of metal. We just talked about glass. Glass is an amorphous solid. A covalent network solid is a diamond. So covalent network solids are extremely strong. So which of the following is an example of a covalent network solid? That's silicon dioxide. You guys know it as sand. Which of the following substance crystallizes as a molecular solid? That's going to be the CH3OH or the methanol. Okay. Butter melts over a range of temperatures, so it's an amorphous solid. So at very low temperatures, oxygen freezes and forms a crystalline solid. This is what they think happened to Apollo 13 when he went to stir the oxygen tanks and it ruptured. That it probably was starting to freeze and form crystallines, and then that's what ruptured the tank. And so it freezes as a molecular crystal. Olive oil solidifies and forms like olive butter. If you put it in the refrigerator, it gets kind of a funky color to it. So it's an amorphous solid. And so if we take a look at the crystalline solid, we already talked about the silicon dioxide being a covalent network. Copper's a metal, so it would be a metallic. Barium sulfate begins with a metal and has an ionic, a polyatomic ion, so it's ionic. And NH3 doesn't have a metal, so it's got covalent bonds, so it's a molecule, so it'd be a molecular solid. If I got a substance that's shiny, conducts electricity, and melts at a relatively high temperature, that solid's probably going to be a metallic solid. If I have a substance that's hard, doesn't conduct electricity, melts at a very high temperature, we're probably talking about a covalent network solid similar to diamonds or graphite. And so we'd end up with D.